So, welcome to this lecture in our course on mechanical operations. In the last class, we talked about primarily drag and inertial transport as mechanisms for transport of particles in flow systems, and we defined certain dimensionless parameters such as the sticking coefficient or capture efficiency, as well as the Stokes number, which is a reflection of how much the transport is dominated by inertia versus other mechanisms. So, Stokes number of 0.1 or larger implies that inertial mechanism is dominant, whereas Stokes numbers of less than 0.1 implies that inertia can be neglected in considering the transport phenomenon. Again, this is important in mechanical operations because particle transport plays a huge role in how processes work in chemical industries, and particularly the flow of particles, the capture of particles, the storage of particles, all of that depends on the particle to particle properties such as adhesion and cohesion, but they also depend on the prevailing macroscopic transport mechanisms that actually convey the particles from one place to another. As I was mentioning in the last class, non-dimensionalization is the key value add that chemical engineers bring, because it enables us to scale. Scaling up and sometimes scaling down is a very important aspect of what chemical engineers bring to industry, but you have to be able to define appropriate dimensionless numbers. So, for example, if you are talking about particle transport and deposition on surfaces, the appropriate dimensionless numbers must reference the prevailing flux of particles to a reference flux. So, the first step then is to define appropriate reference fluxes. And when you talk about transport phenomena in general, they can be classified into two types: quiescent and convective. In a quiescent system, convective flows are virtually absent. This includes natural convection as well as forced convection, and diffusion becomes the predominant mechanism. Whereas in convective flow, clearly there is a significant flux of particles due to the motion of the carrier fluid, and such flows are indicated as convective flows or convection dominated flows, and the reference flux in each case is different. So, in the case of quiescent flow, the reference mass flux, and again we will use this notation where M stands for mass, subscript P stands for particles, dot stands for per unit time, and the double prime stands for per unit area. So, this is basically the particulate mass flux reference value. In the case of quiescent flow, you can write this simply as rho dP, where rho is the density of the carrier fluid, dP is the diffusivity, the Brownian diffusivity of the particle, omega p infinity minus omega p w. So, basically if you have a surface, the surface is conventionally referred to as location W, stands for wall, and the and if there is a fluid flowing past this surface and it has entrained particles in it, and let us say that there is a boundary layer that develops, the location in the fluid outside of the boundary layer is called the main stream or free stream, and it is designated by infinity as a subscript. So, when we talk about omega p infinity minus omega p w, what we are talking about is a gradient in the mass fraction of particles from here to here. So, it is this gradient, and as you know, gradients drive diffusional transport. So, since diffusion is the predominant mechanism here, we have written the reference flux in terms of diffusivity. I mean, this is basically a version of the first law of diffusion, right, where diffusional flux is proportional to gradient in the mass fraction or concentration. The only thing we have done is, instead of a differential form, we have taken the difference omega p infinity minus omega p w and divided it by a reference length. Now, this reference length can be chosen based on the application. For example, if you have a plate of some dimension L, then that linear dimension could be your L, or if it is a cylindrical surface, again either the diameter of the cylinder or the length of the cylinder can be taken as your reference length, depending upon the nature of the transport process that you are concerned about. So, the selection of the reference length changes the absolute value of your reference flux. In certain cases, you can even take it as the thickness of the boundary layer as the reference length. Okay. But most conventionally, this reference length L would be the most easily measurable dimension of your object on which particles are collecting. In the case of convective flow, the reference flux is now given by rho times u times omega p infinity minus omega p w, where rho u is the convective mass flux of the carrier fluid, and when you multiply it by the mass fraction of particles in the carrier fluid, you get the convective flux of particles that are in the suspension. So, once you have defined your reference fluxes, you can proceed to do your non-dimensionalization. So, in the case of quiescent flow, the non-dimensional parameter for particle flux is called the Nusselt number. So, you can write this as nu subscript m comma p, where m stands for mass transfer and p stands for particle, and that will be, so in your denominator you will have mp dot double prime reference quiescent. So, the denominator in the case of the Nusselt number is the quiescent reference flux. In the numerator, you would think that what we should have is the actual mass flux, right, prevailing mass flux. However, by convention, the Nusselt number is not written in terms of the total mass flux that is happening, but the diffusive mass flux. So, instead of mp dot double prime, here we will actually use jp dot double prime, which is the diffusive flux of mass. If you remember the expression we wrote last time for total mass flux of particles, mp dot double prime total, it had several components to it, right. There was mp dot double prime convective plus phoretic plus diffusive, and so this diffusive part is what we are referring to as jp dot double prime. Now, in the case of convective flow, the corresponding non-dimensional number is the Stanton number, which is written as Stanton number again with subscripts m and p to refer to mass transfer and particles. And here, of course, the reference flux will be the reference flux corresponding to convection. But again, interestingly, the numerator is still the diffusive part. Now, both these numbers are functions of flow properties such as Reynolds number and in the case of for mass transfer, they are also functions of Schmidt number. Again, Schmidt number SC equals nu by d, where nu is kinematic diffusivity, mu by rho, and d is diffusivity. So, in the case of a particle, the Schmidt number would be nu by dp. So, the Schmidt number for a particle is written as nu by or SC subscript p, and the Stanton number is also a function of Reynolds number and Schmidt number. And again, the reason for that is the numerator is the diffusive flux, it is not the total mass flux. How are these parameters related to the capture efficiency that we defined last time? You remember we wrote a parameter called capture efficiency, which is a reflection of what fraction of particles that flow across the surface actually get captured on the surface. Is that parameter related to any of these parameters? Actually, there is a relationship. If you remember our definition of capture efficiency, this was the actual flux of particles or actual rate of accumulation of particles on a surface to a reference value. So, in the case of to define this, you have to talk about an MP dot double prime, which is the prevailing mass flux times area of the object. So, this converts it to a rate of accumulation of particles divided by a reference value, which if you recall from last time, we had written it as omega rho u times omega p w minus omega p infinity minus omega p w times A projected. So, if you look at this expression for eta capture and compare it to the Stanton number, how does it look? Well, this divided by this is not exactly equal to the Stanton number, but it is close to it. The Stanton number by definition is the diffusive flux of particles divided by this part, which is basically the same as the denominator over there, but this is different from what we have used in our definition for Stanton number. But in the case where diffusion is the dominant phenomenon, you can approximate this ratio MP dot double prime divided by this whole thing as a Stanton number times AW divided by A projected. Now, in most conventional flow situations, the projected area is roughly half of the total area of the object. So, this parameter is roughly equal to 2. So, very approximately capture efficiency is approximately 2 times the Stanton number in flow situations that are diffusively dominated. Okay. In the case where the flow is not diffusion dominated, but convectively dominated, this number would actually be greater than 2 times Stanton number when this is under conditions where convection is the dominant mechanism. So, there is an interrelationship between these dimensionless parameters. You have to start with the basic parameters. The most basic non-dimensional parameter in any flow situation is the Reynolds number. The Reynolds number is a measure of momentum transfer by diffusion to momentum transfer by convection. The second most fundamental non-dimensional parameters is the Schmidt number, which is a measure of the kinematic momentum diffusivity to mass diffusivity. Once you know those two parameters for your system, you can do experiments to relate the Nusselt number to the Schmidt number and Reynolds number, and similarly you can relate the Stanton number to Reynolds number and Schmidt number, establish correlations between the two, and because you have used non-dimensional parameters, you can apply your results to virtually any flow situation, provided the Stanton number or the Reynolds number and Schmidt number are in the range in which you have done your where your Reynolds number and Schmidt number do not have to be in the range where you have done your experimentation. They can be outside the range as well. But once you are able to gather sufficient data and establish these correlations, you can apply these results over a very broad range of Reynolds numbers and Schmidt numbers and so on. But there is a difficulty. To measure these parameters, Reynolds number is easy to measure. You probably have done some experiments in the momentum transfer lab, or I think you are going to do next semester, to look at Reynolds number measurement. But Schmidt number and therefore Nusselt number, Stanton number are actually very difficult to measure, because we are talking about measuring mass fractions of compounds, particles, which are typically in the parts per million range, sometimes in the parts per billion range. So, these are extremely small values, and it's very difficult to develop instrumentation that can measure such small mass fractions with sufficient accuracy and precision and so on. So, in general, mass transfer parameters are difficult to measure, but what is easy to measure? Heat transfer, because what is a measure of heat transfer? Temperature, right? And we all know how to measure temperature. So, the approach that is used in general in characterizing flows of particulate suspensions is you try to characterize the heat transfer phenomena associated with the flow, and from that you try to extract mass transfer behavior. That becomes possible because of something called an analogy condition. It is called a heat transfer analogy condition. The argument goes that in flow situations where the mechanism for particle or mass transfer is the same as the mechanism for heat transfer, then any correlations that you develop using heat transfer data are equally applicable to the mass transfer process that is happening. So, what is the implicit assumption here? That the mechanisms are the same, that mass transfer is happening by the same mechanisms as heat transfer. When is that possible? That is possible when diffusion and convection are the dominant transport mechanisms. When is the analogy condition violated? For example, if radiation is significant, there is no mass transfer counterpart, so you cannot apply the analogy condition. Or if inertial impaction is a dominant mass transfer mechanism, you cannot use the analogy condition because there is no heat transfer analogy to inertial impaction. A third situation is phoresis, when you have motion of particles due to an applied field. Again, there is no counterpart to that in heat transfer. So, whenever these three phenomena are occurring, when radiation is present in significant amounts, or when inertial impaction is present in significant to a significant extent, or when phoretic phenomena are present because of an electric field or a magnetic field or temperature field and so on, you cannot apply the analogy conditions, but otherwise you can. So, basically the way you would do that is just like you have Schmidt number for mass transfer, you have something called Prandtl number, which is nu by alpha, where alpha is the thermal diffusivity, which is K by rho Cp. K is the thermal conductivity, rho is density, Cp is heat capacity. So, you can estimate the Prandtl number for heat transfer, and by knowing the Reynolds number and the Prandtl number, you can actually obtain the Nusselt number for heat transfer as a function of Reynolds number and Prandtl number, and similarly in convection dominated situations you can obtain the Stanton number for heat transfer as a function of Reynolds number and Prandtl number. Under analogy conditions, NuH as a function of Reynolds number and Prandtl number is identically the same as NuM as a function of Reynolds number and the corresponding Schmidt number, and similarly STH is the same as NuH as a function of Reynolds number and Schmidt number. So that makes it very simple, the functional representation is the same. So once you have obtained the functional relationship in one case, you can directly substitute Schmidt number for Prandtl number and obtain the corresponding mass transfer expression. This makes it very convenient for us to do our experimentation on heat transfer phenomenon and use our data to then draw conclusions about the mass transfer phenomena that are present. This becomes especially important when you have to do measurements sort of in situ, where you do not have the luxury of drawing samples and doing your analysis offline, where you, for example, this may be a flow situation in a pipeline where particles are being conveyed in slurry form, and you need to be able to obtain real time data by injecting a probe right into the flow path. Again, that can be done quite easily for measuring temperature. All you have to do is mount some thermocouples along the walls of the pipe and you can do heat transfer measurements on the fly. But as you can imagine, to do that type of work and measure particle concentrations as they are flowing would be extremely difficult. And so in situations like that, this analogy condition is quite valuable to us as a tool to be able to translate heat transfer data into mass transfer data. By the way, momentum transfer, there is no easy analogy. So you cannot measure momentum transfer parameters such as, what's a typical momentum transfer parameter? Any idea? What's the most fundamental momentum transfer parameter? Pressure drop. In flow in pipes, the most basic measurement that can give you an indication of momentum transfer is measurement of flow rate versus pressure drop. But the problem with that is there is no immediate corollary or analogy to that between that and mass transfer phenomena, except in some very limiting cases. And so people mostly they don't try to measure momentum transfer data and try to relate that back to mass transfer, but it's very frequently done to relate heat transfer data to mass transfer data. All right, so I think that pretty much brings us to an end of the review of very basic processes and principles of particulate flow, I think what the material that we have covered so far will hopefully enable us as we go into more specific mechanical operations to try and relate what is happening in that mechanical operation back to some of the fundamental principles that we have reviewed so far. So just to recap, we first started by discussing the two basic morphological parameters of particles, which is shape and size. So we looked at various methods of shape analysis, qualitative methods, quantitative methods, shape analysis for single particles versus distributions for populations of particles, and from that we transitioned into size measurement, static methods versus dynamic methods, particle capture techniques in order to immobilize particles for static analysis, various methods of dynamic analysis of particle size, methods of static analysis, in particular light scattering and laser scattering based methods. And then after we completed, and of course single particle versus again particle size distributions. The point again being that it is very hard to find particles of the same size in any real system. There is always going to be a distribution of sizes ranging from very fine to very large, and you have to have a way of representing this size distribution in tabular form or in graphical form. You have to be able to evaluate various mean diameters from this data and understand the implications of the differences in the mean sizes. You know, if your number mean size is very different from your area mean size, what does that mean? If you are concerned about light scattering from a suspension, what is the most relevant mean size? You know, it will be the 6th power, right? Because scattering intensity goes as particle size to the power 6. So, you have to be able to match your measurement technique to the application that you have at hand. All right. So, after we covered size and shape analysis, we then started looking at the interfacial properties of particles. Starting with the structure of the particle, which composes of a surface, a subsurface and a core, and the point we made was that the surface participates most extensively in interfacial phenomena, and the 3 interfacial effects that we focused on were surface energy, adsorption and intermolecular or interparticle forces of attraction, the so called van der Waals forces and their equivalent for particles. And after that we looked at the interaction between particles and surfaces. So, we studied the various mechanisms of particle to surface adhesion and the various forces involved in particle to particle cohesion. So, in terms of particle to surface adhesion, we discussed initially the van der Waals forces and the Hammaker constant that describes these forces, various forms of electrostatic forces, surface tension forces, hydrophobic, hydrophilic forces and so on. And then we talked about cohesion, which is the adhesion between particles in a flow or in a suspension, and the fact that many of the forces are common to adsorption to adhesion to surfaces, but some are different. In particular, cohesion is characterized by 3 fairly unique forces that have no counterpart to surface adhesion, that is surface tension forces or capillary forces, viscous forces and spring like forces, right. And then we talked about the effects of these cohesive forces on the behavior of particle suspensions. In particular, 2 aspects. One is when you are trying to gather many discrete particles and bind them together into a single object, such as tablets and capsules in the pharma industry, where what you are really trying to do is maximize the cohesive strength of that tablet. You want whatever that product is not to disintegrate as soon as it is formulated. It has to remain structurally stable until the time it is put to its end use, you know, typically swallow by somebody, by a patient. So, the cohesive strength is an important parameter that we discussed. We also said that in many cases you would want to maximize cohesive strength, but minimize adhesive strength. And so, there are some very subtle considerations that play into how you do that. And the other place where cohesion comes into play is flow. In particular, the flowability of suspensions depends very much on the degree of cohesivity that is present in the suspension. The more cohesive the particles are, the more the system will behave as a 2-phase flow. You will have one continuous phase of the carrier fluid and a second continuous phase consisting of particles. So, when you try to do CFD modeling of the flow, you have to deal with it as a 2-phase problem. Whereas, in the case where cohesion is low, you can look at the particles as discrete entities and actually describe the dynamics of each individual particle in terms of their collisions and rebounding and so on. So, there are some various pluses and minuses to these 2 types of flow analysis, and also various implications from a process viewpoint. Sometimes you want more cohesive behavior in a flow, For example, we talked about discharge from silos, where when you open the gate, you want the material to flow like a solid block, and you want it to behave in a very, very predictable way. Whereas, if you are trying to again pump a slurry through a pipe, you want to minimize pressure drop, and pressure drop increases as cohesion increases. So, in many process industries where you are trying to actually transport the slurry from one location to another, could be from a lower height to a upper height, or it could be through a fairly long distance. You want to minimize any cohesive behavior, so that you can minimize the energy that you have to expend to move the material from one place to another. All right, so after we talked about adhesion and cohesion, the last topic that we covered was the various transport phenomena that affect particle behavior. In the finest sizes, we talked about diffusion, Brownian diffusion as being the predominant mode of transport of particles, particularly in the nano size range and the submicron size range. Electrostatic effects that come into play just above the nano size in the submicron size range. And then in the intermediate size range, you have convective flow, phoretic flow as important transport mechanisms for particles. And in particular, we talked about the situation where drag on a particle is balanced by the gravitational force, and enabling the particle to reach a terminal velocity as it settles through a fluid. And the fact that the terminal velocity, the dependence of the terminal velocity on particle size changes as you go from the micron sizes to submicron sizes to nano sizes. And in fact, the point is, as you approach the nano dimensions, the time that a particle takes to settle can quickly become infinity. It can just start floating essentially in the fluid, right. So, and then in terms of particularly the inertial aspect, we said Stokes number is a controlling parameter, and Stokes number also has a first order effect on capture efficiency of particles on a surface. The higher the Stokes number, the greater the probability of inertial capture. However, if you look at particle capture as a whole, there is actually a non-monotonic behavior. At extremely small sizes, diffusional mechanisms can cause deviation of particles from the streamlines of flow and thereby enhance capture rates. And similarly, at very large sizes, inertial mechanisms can cause departure from streamlines and enable capture. So, as the minimum in capture efficiency is reached for an intermediate size where diffusional effects are weak, but at the same time inertial effects have also not picked up in magnitude. Okay. So, it is very important to differentiate between capture efficiencies due to the inertial mechanism versus overall capture efficiencies, and this has to play into your strategy. If you have a process in which you are trying to minimize particle accumulation on a surface, which sometimes results in material loss in your system, then you have to consider this in a very holistic way and try to minimize your overall loss of material rather than loss of material due to a single specific mechanism. And finally, we talked about other non-dimensional parameters that are used to characterize particle mass transport in flow situations and in quiescent situations, in particular the Nusselt number and the Stanton number for mass transfer, and the relationship to capture efficiency. And finally, we talked about how because mass transfer phenomena are difficult to meter and measure, we try to measure heat transfer phenomena instead, and then draw conclusions regarding the mass transfer coefficients that are prevailing. Okay. So, that kind of is a quick net of what we have covered so far, and in subsequent lectures we will start dealing with specific mechanical operations. We will start with operations that classify particles, that separate particles from a carrier fluid, and later we will start dealing with processes that actually induce changes in the particles themselves, such as size reduction or size agglomeration. Before that, I will also take a couple of lectures to talk about particularly the nano size range. An important aspect of mechanical operations these days are operations involving the synthesis of nanoparticles and the storage and transport of nanoparticles. As we get into mechanical operations as a subject, it is important to understand the qualitative differences in how nanoparticle systems behave versus particles involving larger systems. So, in the next couple of lectures, we will deal with nanoparticulate flow systems involving the synthesis as well as the characterization. In particular, we will look at how mechanical operations can be used to produce nanoparticles. What are known as top down methods. You can take larger particles in the micron size, and just by ball milling them or crushing them, you can actually reduce their size to nano sizes. It is a good illustration of a mechanical operation that is used to produce products that are used in extremely high technology processes, and I think that will give you a good lead into the topic of mechanical operations in general. All right, so any questions on all the material that we have covered so far? Okay, so I will see you tomorrow.